You're so masterful.
You said that right as I missed it. There you go. Hit that sucker. There we go.
All right. Thanks, Gary. Hey, I have a question for you. Do you like it when I review, or do you want me to just go right into the new stuff? You like the review? Okay. I've got mixed. Okay. My attitude is, again, I'm not talking down to you. I'm talking to you like I would talk to a normal geologist, and I realize it can go over your head, and it takes a little while to seep in, or you forget about it. So that's why I like to review, because it's a teaching moment. But obviously, if I reviewed too slowly, then we'd just be in a... Who's the guy pushing the ball up the hill? Who's that? Sisyphus. That's right. Don't want to do that. All right, so reviewing days 1 and 2, we started off with this picture. We noted the two colors, the blue colors of the oceanic crust and the green colors of the continental crusts. And we said very grossly that the ocean basins, I thought it was mine.
Sorry.
The blue color in the ocean basins are underlain by these basaltic rocks, shown here. And this is an oversimplification, but on the continents, shown in yellows and greens, those are more granitic rocks. All right, and these are lighter rocks, and these are denser rocks, and the denser rocks are lower, and that's why we have ocean basins where the water is. And then we said, not only are we looking at this map of the world in terms of the oceanic crust and the continental crust, but we can also see that there's these linear mountain features in the oceanic realm, and we have these trenches along the continental margins, and we can divide the surface of the Earth into these tectonic plates, and these tectonic plates are all defined by one of 3 types of boundaries shown at the top. Divergent boundaries or spreading centers like the mid-ocean ridge or the East Pacific. Subduction zones like we see under South America or under the Lesser Antilles here. Or transform boundaries like we see in our own San Andreas Fault. So all of those major tectonic plates have one of those 3 types of boundaries. And of course, these tectonic plate margins, the edges of the tectonic plates, is essentially where 99% of all the earthquakes in the world occur. So here's the subduction beneath South America, and you have this wide band of earthquakes associated with it, but also you have smaller earthquakes associated with spreading centers, the Caribbean, and so on and so forth. And we also talked a little bit about continental collisions. We talked about the most famous continental collision, which is the Himalayas. And it's basically when you try to subduct one continental crust under another continental crust, it essentially plugs up the plumbing system, and the mountains are created, as shown here. And that's why the mountains are so large in the Himalayas case. So again, you can't subduct continental crust. It's too light, and it plugs up the subduction system. So this is an example of another type of collision. And we noted that we can also form, so a collision is when you have sort of compressional forces. You can also form mountain belts by pulling the Earth apart. So this is the state of Nevada, and these things looking like caterpillars moving north. There is a mountain range associated with pulling Nevada apart and forming this mountain range. So we can form mountains either by collisional forces or compressional forces, but also extensional forces pulling things apart. And then that, of course, leads us to our history of California, which is what the class is focusing on. Here we are here. Here's the San Andreas Fault. To the north of us, we have a nice normal subduction zone system under Oregon and Washington here and up into British Columbia. To the south of us, we have another subduction system in southern Mexico. But in between, we have this San Andreas Fault and this little baby spreading center, little mid-oceanic ridge in the Sea of Cortez in the Gulf of California. And we said that just like you can stick Africa, South America into the armpit of Africa, you can stick Baja California into this notch here in Mexico because it was pulled away from there. On the first day of the class, we hailed Tanya Atwater as this wonderful scholar from Santa Barbara. And Tanya explained the origin of the San Andreas Fault back in about 1970 as the result of the subduction of a mid-ocean ridge spreading center like the East Pacific Rise or the Mid-Atlantic Ridge. So we started off 35 million years ago with a continental margin that looked a lot like South America with just a normal subduction system. But because of the subduction of this ridge system, which occurred right under Los Angeles first, so this point of impact is right under Los Angeles. Here's California. You can see here's California, Nevada. So it's going right under LA. LA is always in the center of things, right? And what happens is as you subduct this spreading system, because of the plate motion vectors, we form the San Andreas Fault. And with time from 25 million years ago to the present, the San Andreas Fault is getting longer and longer and longer. And now it's going from Mendocino up here down to the Salton Sea down here. And it's also about 4 million years ago, we rip off Baja California from mainland Mexico. That was Tanya's theory. And that theory was complemented by this guy, Bruce Leyendijk, also from the same university as Tanya. And he studies ancient magnetism in rocks. And he studied these channel islands off of Santa Barbara. And the rocks had a magnetic signature pointing towards the East Pole. And of course, there is no East Pole. And they realized that these islands had rotated, and they couldn't figure out for a decade or more how those islands could have rotated until Tanya came up with this wonderful movie, which we've seen about 10 times, but we'll see again because we love it so. And what we see is, of course, Santa Barbara originally being next door to San Diego, ripping off and eventually sort of slamming into Santa Maria. All right, in the last 30 million years. So that was Tanya's explanation of how you get paleomagnetic signatures 90 degrees away from where they were, is because Santa Barbara rotated as a block 90 degrees. Then we started to say, okay, well, that's the plate tectonic evolution of the Southern California area and this bizarre history of Santa Barbara. Then we said, well, let's start looking at the rocks around us and try to tie that into the plate tectonic theory. And we said, well, what is around us? And we looked at some of these, the mountain ranges around us from Santa Ana Mountain and San Jacinto. By the way, these will figure prominently next week when we talk about glaciation, these mountain ranges. Did these mountains get glaciated 30,000 years ago? I'll leave it as a cliffhanger so you'll come back. And of course, this is the big San Andreas Fault here. Okay, so we stated that in California, there's basically 3 gross belts of rocks. There's this batholith belt. There's this big basinal extent that's active today as the Great Valley of California. And then there's these blue rocks, along the coastline. And basically what we're seeing is the remnants of the before the formation of the San Andreas Fault, in which we had a volcanic arc, which is the red rocks here. This is the uplifted roots of the volcanic chain associated with the subduction zone. This big valley here is what's called a four-arc basin, and that's this thing here, which is still a valley today. And then this subduction complex is the off-scraped material from the subduction that's going on. And that's the blue stuff here. Now, the fact that you have pink and blue together, that's associated with the motion of the San Andreas Fault. So we said in our area here, like on Catalina, we have some of this Franciscan subduction complex associated with the underthrusting. So today we can go to Catalina and we can stand on the hills of Catalina and we can see blue schist, which is this rock that's formed at very high pressures but at relatively cold temperatures. The idea being that as you subduct rocks, they're pretty cold rocks, but they're at great depth, so we have minerals associated with great depth and cool temperatures, as opposed to underneath, say, the San Gabriel Mountains, where you have a volcanic chain, and at the same depth you might see molten, magma. So again, on Catalina today, we can see the squeezed metamorphic rock, whereas in the San Gabriel Mountains, we'd see more granitic types of rocks associated with a magmatic arc. Then we started talking about cheese and toast, and the question is if the Franciscan rocks, if the rocks in Catalina formed at great depths, like 20 miles, how did they get back up to the surface? And we started to talk about how do you get cheese out from between layers of bread. And we said now you can fold the bread over, but if you fold the bread over, the cheese will still be buried. So in this case, he's squeezing the rocks. This is a cross section through something like this. He's squeezing the rocks together, and this is the cheese here. This would be the bread here, or this is really the Catalina schist, and he's trying to get it up to the surface. And you can see you can't get it up to the surface, but if you pull the sandwich apart, you can bring the deeper rocks up to the surface. So this guy, John Platt, who's a professor today at UCLA, argued that the way you get rocks on Catalina up to the surface is by pulling the crust apart. Well, how do you pull the crust apart? Well, as Santa Barbara is rotating, it's moving away from San Diego, so it's pulling everything apart, and it's right in here that we get the cheese exposed. This is where the Catalina schist comes up to the surface. And as I said last time, I spent hours trying to find an example where they'd pulled a sandwich apart obliquely that looked like the Santa Barbara block. Then this guy, John Suppy, who's a famous Princeton prof, again to this very day, he's still there, they noted that on the islands of Santa Cruz and Santa Rosa, these were the islands that Lyondike studied that had the East Pole. Remember that pointed towards the East Pole? They noted that the rocks here of a certain age are the exact same in appearance as ones in San Diego. So this is that missing San Diego tie that Tanya Atwater talked about. How did they know that Santa Barbara was next to San Diego? Well, these rocks on the Channel Islands look like they're twins. And the question is how did they get up there if they started out down there? And what Crouch and Suppy did is and this is the actual rock that's called the Poway conglomerate, and they suggested this little bend here in their model fits right into that little bend right there. So this is that 90-degree rotation. So that explains that 90-degree rotation that Bruce Lyondike talked about, and this is providing evidence that it really occurred. They're saying that these rocks are chemically identical to those rocks up there. So they're the same rock. And again, this is used to get this Santa Barbara right next to San Diego. Fantastic detective work. Now, Crouch and Suppy also talk about how this was done. So here's our cheese sandwich getting pulled apart. In this case, they're saying that this big red line here is a fault surface, is the actual slip surface. Here's the Catalina schist coming up to the surface, and here's where we live today near the San Joaquin Hills. So this is their interpretation of how the Earth was pulled apart. That was supported by these guys, Robert Bohannon and Eric Geist, and they used basically it's called seismic reflection data, but it's essentially gigantic ultrasound. And they saw that actual fault that was proposed by Crouch and Suppy. So Crouch and Suppy proposed this red fault had brought the Catalina schist up, and Bohannon and Geist actually show you, well, there's the actual fault. We found the fault. So the rocks on Catalina came to the surface, accompanying the Earth the ripping of the earth apart, the extensional tectonism during the rotation of the Santa Barbara block. All right? So when did this ripping occur? And this brings up the dilemma of the, do you remember what I called it last week? It's the problem of the cheese bits. So when do you start seeing little cheese bits, meaning the cheese is now at the surface, so now we'll see pebbles of cheese or pebbles of the Catalina schist. So then what we can do is we can go to Dana Point and Laguna Beach, and you can look at the rocks there, and these rocks are big conglomerates, or they're basically fossilized pebbles from the Catalina schist. So that tells us that Catalina was now subaerial, and rivers were cutting down through it and making these pebbles and boulders and so on and so forth. And here we've got it. So in that the Crouch and Suppy model, they've got the Catalina schist coming up to the surface, and these rocks here in this Miocene San Onofre breccia indicate that the Catalina schist is now eroding and forming these pebbly rocks. And we admired how beautiful people now want to get married associated with the San Onofre breccia. I'm kidding. All right. All right, so the Catalina schist was uplifted during the extension behind the rotating Santa Barbara block, and the erosion of the Catalina schist formed the San Onofre breccia. So what we've done is we've moved this gigantic block, and we're forming this big hole, which is now the Los Angeles Basin. All right, and we filled that basin with a lot of mud called the Monterey Formation, and we can skip this. And this Monterey Formation is magical in that it's an oil-forming rock. And the idea is that, and it's one of the example of it is the white cliffs of Newport Beach. This is the Back Bay, and this white rock here is called diatomite. It's in the Monterey Formation, and it's a chalk, a silicious chalk that is very much prone to making oil. And we said that that was not diatomite, it's not dynamite, but it's diatomite. So that's a silicious chalk. And this silicious chalk, here's actual diatom frustules, they're called. It's formed in an upwelling environment. Nutrient-rich waters come sweeping up to the surface. There's huge fish and plankton populations. They eventually die and fall to the bottom, making organic-rich muds. As the organic-rich muds get buried, they make oil. And that, okay. And we also pointed out that in the Monterey Formation, there's these sandstone bodies. We talked about the sandstone bodies forming underwater. And we talked about turbidity currents in which sand bodies can move thousands of miles underwater, right? I'm waiting to get to the chicken story. Okay, and then it got squeezed. And then we started talking about chickens and how if you heat a chicken up, it gets greasy at a certain color. When a chicken is brown to golden brown, it gets greasy. And we said that that's basically the same schedule that they use for predicting when oil is formed in the subsurface. They look at the same color range, and they say, well, these rocks are now making oil. So it's the same scale as you'd use for kitchens. And so the idea being that when rocks get to the right temperature, oil forms and it bubbles up through the existing water in the rock, and then it gets trapped, and we form oil reserves. So in this Monterey Formation, we have one of the densest occurrences of oil fields in the world, as we discussed last time. So here's all the oil fields in the Los Angeles Basin. So remember, we've got the Santa Barbara block. It rotates. The blue schists come to the surface, and you get eroded, and they form this basin. And this basin fills with the organic-rich mud. It gets squeezed, and it forms tons and tons of oil. And of course, Los Angeles was famous at the turn of the 20th century for being a big oil center. Before Houston or anything else, everybody came to LA for these giant oil fields. and then went to other places, of course. So here's all the wells that have been drilled for oil in the Southern California area, thousands of them. And we looked at Signal Hill, which is a wonderful little hill that we all know about near the freeway, and that used to be covered with oil derricks. Huntington Beach used to be covered with oil derricks, and so on and so forth. Good enough. So at any rate, that was just a little brief refresher, and I didn't want to spend too much time on it. But we're going to use that same framework to now look at earthquakes. All right? Jumping ahead. Okay, the first thing we have to do is review faulting. Okay, faults are breaks in the earth. So whenever there's tectonic forces that are pushing hard enough on rocks, they will break. So it's you can take a dinner plate, and if you squeeze it hard enough, eventually the dinner plate will break. So geologists define essentially 3 different types of breaks in the earth. If you squeeze rocks together, you'll get what's called a reverse fault. So this block moves up relative to that block. If you pull rocks apart, like as under the case of gravity, they will be separated, and this is called a normal fault. It's called normal because gravity tends to push down on things, and that would tend to cause this type of motion. And then strike-slip faults, like the San Andreas, are this type of motion. So normal fault, reverse fault, strike-slip fault are the 3 majors. This is just a combined version. All right, here's what they look like in a field. So here you're walking down a field, and here's a fault right there. And you can see that obviously they didn't plow this field to have it offset there. Those lines were originally like that, and then they were offset. So what type of fault would that be? Strike slip, very good. This type of fault, that green unit here, this is a cliff face, there's a human. This is a green rock here, it's a green rock here. So this is gone from here down to there. Here's the fault. Can you tell what type of fault that is? Right, you guys are on fire. And here's this brown rock or this rock here, and here's a fault like that. What type of fault is that? Wrong. Right, no, it's still normal. If you look, it's the exact same thing, just flipped over. I couldn't find a picture of a reverse fault was the problem. No, so this fault is, that just flipped the fault plane direction. I apologize. I tried to find it. I couldn't find one. All right, now let's do this is a little bit more speculative. If you're in this type of environment, in a subduction zone environment, what type of faulting might you expect? Would you expect strike-slip faults, reverse faults, or normal faults? Reverse. You're squeezing things together. You're pressuring. You're pushing things together. You're pushing things together, so you get a reverse fault. In a transform fault, which would be, and then mid-ocean is where you're pulling things apart. And you can see these are all little normal faults there, too. Good job. So transform would be strike-slip. Squeezing together would be the subduction. And pulling apart would be the mid-ocean ridge. Okay, now let's talk about faults in Southern California. Here's some of our big fault systems. Here's the San Andreas. This is the San Jacinto, Elsinore. And here's the one we're going to focus on today because it's our own little fault. This goes into the Rose Canyon fault down there. But these are the bigger, so they have different colors here, but there's lots and lots of faults, right? Southern California has its faults. This is another very funny geology joke. All right. I thought I had another picture. All right. When faults slip or move, there's earthquakes. So here's a fault plane. When it moves, it causes an earthquake. Okay, so the motion on a fault causes an earthquake, and here's, I think, the Northridge fault, or earthquake. Okay, earthquakes, there are big earthquakes and there are little earthquakes. So most of you heard about the Richter magnitude scale, and if we said it's a 3 or a 9, you have a feeling of what that means. But, and we also know that earthquakes occur on faults. What else do you need to know? Did you know there's different types of earthquakes? All right? And what does the Tanya Atwater model tell us about our earthquakes in Southern California? So those are some of the things we're going to talk about today that I hope are new to you. Okay, faults in Southern California. Here's what I was looking for. What they've done is they've color-coded these based on their length and their history. They're saying, we think we can predict grossly how big of a Richter magnitude earthquake can be associated with those faults. So on the black guy, they're saying maybe an 8 on the San Andreas Fault. On the red guys, they're saying 7.5 to 8, which are devastating earthquakes. And then orange would be 6, 7, and yellowish would be 6, 7, or unrated. This is some of the things that seismologists do for the public is to do this sort of study where they're giving you a safety recommendation. Okay, what is an earthquake? This is going to be a bit of a review to you. An earthquake is what happens when two blocks of the earth suddenly slip past each other. The surface where they slip is called the fault or the fault plane. The location below the earth's surface where the earthquake started is called the hypocenter, and the location above it is called the epicenter. So the focus or the hypocenter is here. That's where the actual earthquake occurs. Epicenter is where it's the nearest place on the surface of the earth. Here's the fault. And what type of fault is that? We're getting a mixed answer. So basically, we're pushing like that. This side's moving up, so it is a reverse. Notice that we've got a little hillside here called a fault scarp. So even though the fault's happening down here, you're getting a zone of uplift here where you can see what's called a fault. So if it's actually a linear hill, and this is, of course, what you can see on satellite images and so forth, are these fault scarps. Okay, I just asked you that question, and we decided it was a... Thank you. Okay, here's some entertaining videos. This one is an overview from National Geographic. Little quick, it's about 3 minutes. Nope. It's 1 minute, 10 seconds. No, that's an advertisement.
If you ever find yourself...
There we go.
The ground starts to quiver, shifts, and everything begins to collapse.
I'm skipping the intro.
Some of us may have even lived through one. And we know they can be deadly.
Is everyone here?
But where does this mountain moving force come from? While we may think we're standing on solid ground, the Earth beneath us isn't completely stable at all. Our planet's crust is made up of about 12 major tectonic plates that fit together like a giant jigsaw puzzle. These huge slabs of land float on superheated magma and constantly shift, bump, and grind against one another. It's there, along the seams, where earthquakes tend to happen. When friction between the two plates is violent enough, seismic shock waves ripple through the ground, rattling everything that stands on it. The stronger and shallower the quake, the more violent the destruction. The most violent type of earthquake is born in a subduction zone, where one tectonic plate is shoved beneath another. While one plate is forced downward into the mantle, the other juts upward, often violently. This is the type of quake that rocked Nepal in May 2015. And when subduction happens under the ocean, it can create giant, unstoppable waves called tsunamis, like the ones that killed hundreds of thousands in Japan and Indonesia. On average, earthquakes kill about 10,000 people each year. Sometimes numbers are far higher. The quake that hit Haiti in 2010 killed more than 300,000 by some counts, making it one of the deadliest on record. It is estimated that there are 500,000 detectable earthquakes in the world each year. 100,000 of these can be felt, and 100 of them cause damage. That's about 0.1%. The magnitude of an earthquake is measured using the Richter scale, which runs from 0 to 10, 10 being the strongest. Every whole number increase on the scale means 10 times more ground motion change. In recorded history, the world has never experienced a 10 on the Richter scale, but scientists predict an average of at least one major quake of magnitude 8 or higher every year. The fact is, the Earth's crust is restless and always on the move. We can't see earthquakes coming, but we can prepare for them. Engineers are now designing stronger buildings resilient enough to survive a direct hit. Scientists are crunching data to project the power of future quakes and anticipate when and where they could strike next. Right now, we can only estimate the probability an earthquake will occur, but perhaps one day we will learn to predict them, minimizing their destruction and saving countless lives.
All right, a quick one. Yes?
I'd be remiss if I didn't mention that we spent a lot of time in these classes convincing people that the Richter scale is no longer used. It's the
We're-
moment magnitude scale.
No, we're going into that.
Okay, yeah, that's a little misleading to,
Oh,
to our group, our sophisticated.
all right. I love this video. This is on swimming pools and earthquakes. So here's some guys happily swimming and then the earthquake. It's amazing how large of a wave you can get in a swimming pool that small. That's like looks like a 3-foot wave. Yeah, where's the boogie boards? But wait, there's more. It's amazing how big of a wave you can get in such a tiny area. All right, lovely stuff. And what's this one? Oh, earthquake safety. This is my tribute to earthquake safety. And someone mentioned this before class.
The critics agree.
Oh,
Renee
God,
Zellweger
sorry.
gives the performance of the year. Astonishing.
All right. Okay, a little statistical question. How many of you have bolted in your bookcases at home? Have you all? That's the first thing I always do whenever I move. All right, recording earthquakes, seismographs or seismometers. A seismograph or seismometer is an instrument used to detect and record seismic waves. Seismic waves are propagating vibrations that carry energy from the source of an earthquake outward in all directions. They travel through the interior of the earth and can be measured with sensitive detectors. So essentially you've got a thing hanging here, and this is rolling around, and this pen is shaking as the earth shakes. And you can see this is the recording. The first thing that you see is called the P wave, then the S wave, and then the surface waves, and we'll talk about that in a minute. Okay, this is the big one, earthquake waves. I went out and I purchased a thing to demonstrate earthquake waves. Just hold that in. And this is the standard. I found this on Amazon. It was like $4, so I'm very happy with this. So there's two basic types of waves. There's body waves and surface waves. Body waves are waves that occur inside the medium. So sound waves are body waves. You're hearing my voice going out in all directions. A surface wave only moves on the surface, like a wave on the ocean. All right, so there's two types of body waves, a P wave, or a primary wave, or a compression wave, and then an S wave, a shear wave, or a secondary wave. A P wave moves in and out like this. Actually, I'm going to do this a little bit longer. Everybody see this, maybe? Stand this way. Come to the audience, or come so the...
Turn on the lights for a second.
Oh, you guys, you want everything. All right. All right, so here's our slinky. We're all set, right? Okay. Okay, so this is the P wave. All right. Okay, now a shear wave is one that goes like that. All right. Now, an S wave, now in vector math, they can talk about a vertical shear wave and a horizontal shear wave. So they commonly break the S wave into two. But at any rate, this is so the P wave is in and out like that, and then the shear wave is going side to side like that. All right? Thank you for that help. Now, it turns out that the P wave, I was checking, the P wave actually goes about twice as fast as the shear wave. So that's why it arrives first, the P wave. But I was just checking with this, and they look to be going about the same speed, so that didn't work out. Okay, so body waves. Here's that P wave. They're basically showing the slinky here. And they're saying it's a little compressed here and expanded here. So that's the P wave. And then here's the S wave, and it's moving up and down like that. Okay, the amazing thing about P and S waves is as follows. P waves can go through fluids, and S waves can't. So S waves cannot exist in fluids. It has humongous implications. All right, so the two types of body waves. Okay, S waves, P waves, solid only. Again, solid. Let's see, this is confusing. Surface waves, body waves. Oh, they're just saying something else. All right, and then here's our surface waves. There's two types of motion. There's shearing, and then there's vertical motion. These are called love waves, which is, of course, very entertaining to, young college students. And Raleigh waves down here, which are the other form of surface waves. So these are only occurring on the actual surface of the Earth. And then these are what's happening inside. Why can't S waves travel through liquids? S waves are shear waves where particles move perpendicular to the direction of propagation. Liquids don't have shear strength, so a shear wave can't propagate through a liquid. This has the following profound implications. If we have a giant earthquake here, and you track the path of the P wave, because we know from these studies that the outer core is liquid, the P wave is going to change direction because it'll slow down in the outer core, and we get these shadow zones associated with the P wave. In the case of an S wave, because of this outer core that's liquid, this whole area, you can't see the S wave. All right? So one of the most important things we learned about seismology is the fact that we have this molten outer core because of this S wave shadow zone, and also this weird pattern where you have these dual shadow zones associated with the P wave. This is one of the most amazing discoveries in the seismological hemisphere. But this was discovered, 100 years ago. But it's still amazing. Does that make sense? So P waves tell us about the outer core because the P waves slow down going through the fluid part, and you get these shadow zones. And then the S waves can't go through fluids at all, so we get this enormous shadow zone associated with it. And that's how we know a lot about the interior of our planet. Again, this is showing the P wave shadow zones here, and then the S wave shadow zones here. What types of waves are sound waves? P waves. Are you hearing any S waves? Am I shouting S waves at you? You're not hearing any S waves because S waves can't go through fluids, and air is a fluid, right? You talking to me? That's, simple. All right, let's do a little review here.
It's time
after a commercial.
to play the music.
All right, here we go.
It's time.
The motion we feel on the surface of the Earth during an earthquake comes from energy released deep within the Earth. This energy is transmitted to the surface by earthquake waves. The study of earthquakes and earthquake waves is called seismology. Earthquakes occur when rocks deep underground suddenly break under pressure or slip along a fault. The point of release is known as the focus of the earthquake. The energy released by the earthquake radiates from the focus as body waves. There are two types of body waves. The fastest wave is called a P wave, or primary wave. It moves between 4 to 7 kilometers per second, depending on the density of the rock it's moving through. A P wave is a compression type wave. Rocky material in its direction of travel compresses, then expands as the wave passes. A P wave is similar to a wave traveling through a spring. The coils compress and expand in the direction the wave is traveling. The second type of body wave is called an S wave, or secondary wave. It travels at about 2 to 5 kilometers per second through rock, about half the speed of a P wave. An S wave is a transverse shear wave. Rocky material in its path moves up and down, or side to side, perpendicular to the direction of the wave's travel. An S wave is similar to a wave traveling along a piece of rope. The wave moves along the rope by moving a section of the rope up, then down. Surface waves radiate outward from the epicenter, the point on the surface closest to the focus. Surface waves are slower than body waves, traveling at 2 to 3 kilometers per second. They can change the surface of the Earth as well as damage homes, buildings, and other structures. There are two types of surface waves. A love wave causes side-to-side motion perpendicular to its direction of travel. It can cause damage by breaking roads and pipes. The second type of surface wave is called a Rayleigh wave. It moves the surface of the Earth up, forward, down, and back in a circle. It can cause damage by knocking buildings off their foundations. In most earthquakes, combinations of love and Rayleigh waves cause the most destruction because the ground shakes up and down and side to side at the same time.
Alrighty. See what this one is.
Earthquakes generate two main types of seismic or shock waves, body waves and surface waves. Body waves travel through the interior of the Earth. The fastest of these are primary or P waves. These compressional waves move faster in dense rock and slower
And here's the
in
shadow
fluids.
zones.
Thus, their speed and direction change. Because they are deflected by the Earth's core, P waves are not seen in the so-called shadow zone. The slowest body waves are secondary, or S waves. S waves are elastic shear waves that move material sideways at right angles to their direction of travel. Because secondary waves travel only through solids, they do not penetrate the Earth's outer molten core. For this reason, there is also an S-wave shadow zone. The slower seismic surface waves do not penetrate the Earth's interior, but follow the surface. One type of surface wave, the love wave, travels in a circular motion and causes damage by displacing materials horizontally. Love waves can be very damaging. This cracked pavement and these twisted railroad tracks clearly demonstrate their destructive power. Earthquake damage also results from Rayleigh waves, surface waves which deform materials vertically.
All right. We talked about this previously. Earthquakes are tied to plate boundaries, so we can march on. And we also talked about this previously, where we noted that the deepest earthquakes, so black is shallow, green is intermediate, red is deep, are associated with subduction zones. Right? So to get a deep earthquake, you need a subduction zone. So one plate, this cold plate is being thrust underneath the other plate, and that's how we get our deepest earthquakes. And we mentioned this previously, earthquakes and plate tectonics transform subduction zone and mid-ocean ridge, so we'll skip that one and get on to this question. How do seismologists locate earthquake epicenters?
Let's locate the epicenter for an earthquake that takes place in the United States. This is a seismograph from Salt Lake City.
Can y'all hear?
Here's where the P wave arrived. It was 1 minute.
Okay.
Here's where the S wave arrived.
P wave arrives, S wave arrives 4 minutes, 1 minute, 4 minutes.
Arrival time for the P wave was 1 minute.
Arrival time for the P wave, 1 minute. Arrival time of the S wave, 4 minutes.
So then the difference in arrival time for the P and the S wave
What's the difference? 3. Very good. You guys are on fire.
is equal to 4 minutes
Minus 1 minute.
which is
There we
equal
go.
to 3 minutes.
All right.
Okay, so we know the difference in the arrival time. That's all we need to know to come to the P and the S wave chart here and to find out how far away the epicenter was. So I measure out 3 minutes.
So he
over
measures out
here
3 minutes
on
here,
the
and then he just
scale
slides this
4
up
times. See
until
that?
it fits in
Now I
between these.
slide
This is the
along
S wave curve.
P
This
and
is
the
the
S
P
wave
wave
chart, so I find
curve here,
exactly where
and that tells you how
3
far away the
minutes fits.
epicenter distance is. See that? So he's
There.
sliding the
See
red
that? I
bar up
drop
here,
a line straight
and he
down
says
that
it's
little
about
dotted line, and I found a
2
little box around it. That's 1,800 kilometers.
1,800 kilometers.
Therefore, we now know the city is 1,800 kilometers away.
So based on the difference between the P wave arrival and the S wave arrival, they know that the location of the earthquake is 1,800 kilometers away from the epicenter. What's the problem? You don't know. It's in any direction. It's a circle around you. All right? So how do you solve that, by the way, you sharp people? What's that? A second circle, how many intersect? If you have 2 circles and they intersect, how many intersections will you get? So you need 3 you need 3 seismic stations, so there's the answer. Sharp.
From the epicenter.
Okay, we'll just skip.
So I go to my map right here. Now, if you look right up here at the top of the map, there's a scale.
Yeah, we
I'm
know
going
what
to
your
measure
scale.
out 1,000.
All right, so, and he's going to draw a circle. And he's still
I'm
drawing
going
the
to-
circle. He's really slow
That's
drawing. Yeah, okay, there's the one.
1,800 kilometers. I've labeled it.
1800.
Now, if I were to draw a circle,
But now he draws the circle.
anywhere on that
So
circle,
somewhere
we could
around
add
there is the epicenter.
the earthquake.
All right.
We don't know where.
But now he can do
I
it for
measured
another
that.
area, as we've talked about. So here's
Now,
another one. Now you have
narrow
2 possible
down
locations
how
of the
many places
earthquake.
The earthquake could be to one
Right?
of these
Does that
2
make sense to everyone?
spots.
And then, obviously,
Then you
with
put
3.
one spot on the city, Anna,
And then,
draw our circle.
then
As you can
there's the
see,
3rd. And
all
now
3 of
this
these
is the
circles
answer.
Now intersect in one spot.
All right, so that's how you locate an earthquake. How big was that earthquake? What's the humor? Well, it's all computerized now, so. We usually talk about earthquakes in terms of their size. There's different ways to characterize earthquakes. There's essentially 2 ways to characterize an earthquake's size. It's either its seismograph or seismometer behavior, or how people describe it. And you might think, well, this is a machine, so it must be better. Why do you think? Why is this sometimes better? Because you're there. But there's one thing between these 2 things, a big difference. This was invented. This was not invented. This is just people. So you can go back before there are seismographs and do earthquake studies. So the neat thing that you can do is, based on the description, is you can go back and look at newspaper clippings and so forth, and you can figure out about earthquakes, even though there was no seismometers at the time. So anyway, earthquake magnitude. We'll talk about the Richter magnitude scale first. Gary doesn't like it, but he's a local guy. Charles F. Richter was at Caltech. So we have to appreciate that. And here's some information on the Richter magnitudes. So again, we go from scale from... So the Richter magnitude does not stop at 10. It's the power of 10. So it could go up to 20. I mean, you'd probably vaporize the planet by that time. But this it's not like a numeric scale that's formalized. It's based on, it's essentially a number in an equation. All right, so there's nothing magical about 10 being the highest. All right, so the number of earthquakes per year is a function of their magnitude, the Richter magnitude here. So there might be 1 million magnitude earthquakes per year, but only 10 magnitude 7 per year. So these are much more common, these are much less common. But on the other hand, when these things go off, equivalent in kilograms of explosion, this is 100,000 million, billion, trillion. So like a 10 is like 56 trillion kilograms of explosive, whereas the magnitude 2 is like 56. Well, then the smart ones among you, might say, well, you have 1 million of these, and you only have 1 of those, so don't they kind of even out? And the answer is, like, 1 million times 56 is 56 million, 100,000 million. So that's about the equivalent to a 6, right? So 1 million magnitude 2s is about the same in terms of explosion related as a magnitude 6, right? Okay, how do you calculate a Richter magnitude scale? Again, this has been surpassed by the more modern version, but let's still look at the Richter magnitude scale because it's kind of interesting. I never knew this. I had to find out on a YouTube video myself.
They'll have asthma the rest of their lives.
Not another one.
But some in Washington want to let insurance companies deny them coverage because they have a pre-existing condition. Not Katie Porter.
Not
She's
Katie
fighting
Porter.
to protect
Yay,
healthcare for people
she's
with
local.
pre-existing conditions. Thank her for leading the fight.
Thank you, Katie. All right.
How to determine an earthquake's Richter magnitude. In 1935, geologist Charles Francis Richter devised a system known as the Richter scale. This scale measured the energy output of earthquakes, ranging from a value of 1 for the weakest earthquakes up to a value of 10 for the strongest. You can see the scale here. In this video, I'd like to show you how we go about calculating the Richter magnitude of an earthquake. To begin, we must have a seismogram. So imagine for a moment you're sitting at a seismometer and an earthquake happens somewhere in the world, and your seismometer gets this reading. So let's do some analysis of this seismogram. First of all, the first jump is always going to represent the arrival of the P wave, or the primary wave, and the second jump is going to represent the arrival of the secondary wave, or the S wave, seen here. This line is what we call the baseline, and that's what we're going to compare the height of the waves to. We can see that there has been a 30-second difference in the arrival of the P wave and the S wave on this particular seismogram. We call that time the lag time. Additionally, we will need a scale that tells us how high the highest S waves reached for this particular earthquake. In this example, we'll say that the highest S wave reached a height of 23 millimeters above the baseline. Now, before we can calculate the Richter magnitude, we need to do a little bit of work. And the first thing we want to do is figure out how far away from the earthquake's epicenter our location is. And to do that, we need to look at the lag time, which in this case is 30 seconds. Let's pull out our travel time chart
So
and a
this
piece
is the
of scrap
same
paper
chart we looked
and
at
mark off
previously,
that
right?
lag time. All we need to do now is wedge it in between the two curves until it fits. At which point, we go down the edge of our scrap paper and notice that the distance is 210 kilometers. Let's add that to the list of information we know. Now, in order to find the Richter magnitude, we will need that epicenter distance, and we will need one other piece of information, which in this case is the height above the baseline, ours being 23 millimeters. So, let's keep those two pieces of data in mind, and let's bring in the chart we need to calculate the Richter magnitude. It's kind of a bizarre looking chart. Let me show you how it works. Notice I've color-coded our pieces of data. So the pink dot is going to represent our epicenter distance, which we calculated to be 210 kilometers. And our blue dot is going to represent the height of the largest S wave, which in our case was 23 millimeters above the baseline. We simply need to plot those 2 points on the left and right axis of this chart as such. You'll notice the pink dot is at a distance of 210 and the blue dot is at a height of 23. Now all we need to do is use a straight edge to connect those 2 points, and wherever we cross the middle axis, the Richter magnitude axis, that is our Richter magnitude. So this earthquake has a Richter magnitude of 5.0.
Now, of course, they're doing this with computers today and so forth. They don't use pencils and papers anymore. Okay, as Gary said a minute ago, nobody uses, well, they use the Richter magnitude scale now, but they usually, but mostly historically. But they also talk about the moment magnitude, and this is, as stated here, is measures earthquake strength based on the amount of energy released by calculating the size of the fault, the amount of motion, and the type of rock stiffness. The moment magnitude scale is preferred over the Richter scale by seismologists. It's more accurate, they believe. When hearing about an earthquake on the news, this is typically the final, most accurate magnitude given. Fortunately, though, the numbers are kind of similar. All right, so they're not too, so it's not like this is a 9 and this is a 2. They're always kind of in the same ballpark. All right, the Mercalli. Remember I said there's 2 types of ways of measuring earthquakes. One's using the machine, the seismometer, and the other one's by talking to people. The Mercalli is the famous intensity scale, and instead of saying 1 to 10 Richter magnitude, we can go 1 to 12 Mercalli. They use Roman numerals here. 1 is not felt, 2 is felt by persons at rest, on upper floors, felt indoors, vibrations, feels like a heavy truck going by, felt outdoors, felt by all, difficult to stand, partial collapse of masonry, masonry seriously damaged, and so on and so forth. So again, this is powerful because you can go back in time and evaluate histories before there were seismometers. So here's an application of the Mercalli scale to the San Francisco earthquake of 1906, magnitude 7.8, based on historical analysis. This is the fault scarp. So that entire area moved during the earthquake. It's a very large earthquake, and this is showing the damage using the Mercalli type of approach. But remember, there was no seismometers back then. This is all based on historical calculations. The USGS has more modern techniques. This is called a shake map, and it's based on seismogram. So here's where the earthquake is, and they're showing relative amounts of shaking, but using seismogram data. So here's a shake map associated with this earthquake here. This is called a DYFY, did you feel it? And it's kind of like the Mercalli approach, where you talk about what type of, how you experience the earthquake. And again, you can map it out like a Mercalli approach. There's a very important relationship between the magnitude of the earthquake, the size of the earthquake, and the length of the fault. So if the fault is a little short fault, it will never have a 9 on it. To get a magnitude like 8 or a 9, you need a really long fault, 100,000 miles. So this is the surface rupture length. So the fault's going to move 100 kilometers of motion. I mean, so the fault might move, 6 centimeters, or maybe, say 50 feet, but it's doing it over 100 miles of length, and that might be an earthquake that's a 7. All right? So the length of the break is correlated to the strength of the earthquake. Does that make sense? Here's an example of California seismic stations. This is where we get our data for earthquakes. And this is not the last 7 days. This is a thing I did a while back. You can go to the USGS right now. I'll show you how to do it. And you can learn about earthquakes. This looks like that little cluster we had a few months ago near Ridgecrest. Okay, here is the actual earthquake site that you can go to. I'm clicking on it here. And what you can do is you can go to earthquake catalog, search earthquake catalog. Then you can say, I'm going to do a custom one, and I'm going to do oh gosh, I can't tell you how many times I've done something like that. Okay, so here we are zooming in on Los Angeles. Then we make a box around it. Oop, we make a box around it like that. And then we say use this region. And then we say past 7 days, anything that's greater than 2.5, let's search. And that's all right. And then we go to I'd have to start over. Okay, there's no offense. No. Check your setting. That's what I want. We come down and magnitude. Oh, here it is. Well, let's do 30 days. Oh, I'm sorry. It always takes me a few minutes to figure this out. Yeah. Never mind. But I do have some results here. So here's the this is what the results would have looked like. This is showing all the faults in the USGS database. This is showing famous local earthquakes greater than a magnitude 7. So those are shown here, here, and here. This was in Ludlow, California, 1999, a 7.1. Landers, 7.3. And Grapevine, this is the White Wolf Fault one in 1952. This is the second largest earthquake, I think, in California, 7.5. If you do the same area greater than 6, here's Grapevine. That's that same 1952 one. here's here's the Long Beach earthquake. I think these are the two, Silmar and Ridgecrest is over here. Northridge and Silmar, I think, are these two, and so on and so forth. So anyway, I'm going back. Okay, here's greater than 7, there is 3. Greater than 6, there's what, about 10. Greater than 5, now there's about 40. Greater than 4, all right. Greater than 3, all right. And I think I couldn't do greater than 2 because it would fill it, yeah. So now some of the interesting things is there's sort of these gaps in here, and happily we're in one of those gaps. That's basically, here's the Long Beach earthquake right there from 1933 that we'll talk about. But this area down here where we live is kind of an earthquake-free zone, which is nice. Yeah.
At that point, if we are in one of those gaps, we certainly felt that earthquake just a few months ago.
But that happened somewhere else. That we can still feel the earthquakes, but the question is, will an epicenter be here?
Oh, okay.
Okay, this is the location of the earthquake epicenters. And again, this is supporting this interpretation here that there's a lot more smaller earthquakes than there are bigger earthquakes. By the way, a guy I used to work with a seismologist I used to work with used to argue that whenever you saw a gap, like this one down here, that's where the next earthquake's going to be. That was called the earthquake gap hypothesis. Good point. Okay. I'm going to do something really, really cool next, so take a break. Fault that I'm looking down right here. This is the San Andreas Fault, and I am the earthquake. All right, and we know the type of motion on the San Andreas Fault? Like this, right? Okay, so I am the center of the actual crack. All right? And because of strike slip, we're going to move like this, right? Right? So during the earthquake, I'm going to go like this, right? Okay, so if you were in front of me, I'd push you. If you were behind me, I'd pull you, right? If you were behind me, because we're moving this way, because I am the actual fracture, I'm pushing you in that direction, but I'm pulling you behind me, and I'm pulling you on this side, and I'm pushing you behind me. All right? So we can say that in this fault plane, we can define compressional zones and extensional zones. All right? Now, the weird thing about it is you can't tell, because it's compressional, extensional, the fault could be going in this direction and give you the exact same answer. Okay, so one of the weird things about these things called focal mechanisms is they can tell you about the nature of the fault, but they don't really know where the fault plane is. All right? So the way they do this is they show these things. These are called beach balls because they look like beach balls. And what I just showed you was this would be the compressional zone here, and this is the extensional zone here for the fault here. And you can define how the actual earthquake moves. So the thing is they can study an earthquake and they can say what the slip was on it. Now the weird thing about this is, imagine now that the fault plane isn't running like this, but it's actually horizontal. Okay, and now I'm lying on my side. The same thing applies. So the orientation of the fault plane doesn't make any difference. Any orientation will have the same behavior where you'll have a push zone and a pull zone. So what they do is they plot this in. Basically, these beach balls are the lower half of basketballs. And the fault plane would be like this or like this, and then they'd plot the different shapes. This would be for a thrust fault or a reverse fault, a different shape of the beach ball, and this is for a normal fault. So you can actually tell, based on taking all this seismologic information, how the actual fault plane moves. The weird thing, again, is you don't know where the fault plane is. It could be that direction or that direction, but usually there's other geologic information that tells you, if you're seeing this, you'd say, well, that's the San Andreas Fault. Give me a break, right? So in almost all cases, we know where the fault is, but they don't know officially just based on the beach ball. So this concept of focal mechanisms, and it's just a wonderfully powerful way for analyzing earthquakes. Okay, so there is a strike slip, and that would be the beach ball associated with it. normal fault, and so on and so forth. And as I mentioned, you can't tell, you have two solutions for the orientation of the fault plane that we'll need other information for. Okay, enough of the animation. Okay, this is just summarizing again. This is the strike-slip case. It looks like that, where you're looking down on the beach ball. Here's the normal fault where the white's on the top, and the reverse fault where you have the black on the top. All right? And you're thinking to yourself, why is he telling me this? And I said, because we're going to use this. I'm freaking out with the lights there. Okay. All right. All right. So here we are in Southern California. Here's our own fault. What's the name of it? Newport Inglewood. And according to these beach balls, they're saying that this is a strike-slip type of fault. So here's a 3.4 magnitude, a 3.3 magnitude, and they're saying that that's the fault plane, that's the fault plane, and they're getting a little bit of, it's not a perfect strike-slip, it's a little bit, inclined in this case, but in general, that's supporting this orientation like that and that strike-slip of motion behavior. Isn't that wonderful? So it's definitely not looking like this. Here's the San Andreas, fits perfectly. It's definitely not looking like the normal and reverse faults. Okay, now we've got a new way of looking at the Tanya-Atwater model. All right? What type of focal mechanisms would you expect from Tanya's animation? So what do you think is going to be happening here? What's happening up in Santa Maria? Things are getting compressed, so we'd expect to find lots of earthquakes with reverse faulting here. Here's the big old San Andreas, so we'd expect to see San Andreas type motion, strike-slip motion. And here you might expect to see extensional motion, except for most of the extension is kind of dead. So we can now take the Tanya-Atwater model and say, I predict, based on Tanya-Atwater models, that we'll see strike-slip and thrust faulting in the transverse ranges. We'll see strike-slip near San Diego, and we might see extension in the basin, Catalina Basin, but actually we know that's also been squeezed a lot too more recently. And here's the actual results. Here is Los Angeles. Here's Palos Verdes. We're down here. These are a whole bunch of beach balls, the focal mechanism balls, associated with the Santa Monica Mountains. And what they're telling you here is you're seeing lots of reverse faulting. So that fits perfectly with the Tanya-Atwater model, that the Santa Barbara block is getting kind of squeezed as it rotates in, and now we're seeing lots of reverse faults associated with it. Right? Isn't that cool? Okay, this isn't even, but the thing is in the olden days, every one of these beach balls, I think, took like a day or two you had to like figure out all the different motions and on the seismographs, and it took a long time to come up with these answers. But now with computers, they can do things like this, where every one of those little colored dots is a solution of a focal mechanism, and we can read about it. And so here's Los Angeles, here's Palos Verdes, Catalina here, and we can see that out here from the Salton Sea to San Diego, we're seeing lots of red and green, which are normal faults and strike-slip faults here. As we go north of Los Angeles into Ventura, where the Santa Barbara block's slamming into Santa Maria. Here's the transverse ranges here. We're seeing lots of black, which are the reverse faults. We're also seeing red, which are the strike-slip faults. All right? So now we can take the Tanya-Atwater model and say, does it help us understand the distribution of earthquakes? And the answer is yes, it does. Now, the reason we don't see extension out here is because things got squeezed after the extension happened. All right, so this is focal mechanism from 13,000 earthquakes. I'll tell you, he did this by computer, not by plotting every single one. All right. So focal mechanisms seem to support the tectonic model of Tanya-Atwater. All right, let's look a little bit more at some of these faults. This is called the Palos Verdes fault that separates the Palos Verdes hills / mountains from, say, Torrance and San Pedro. Here's our own Newport Inglewood Fault. The funny thing about the Newport Inglewood is it's not really a through-going fault. It kind of has lots of little branches associated with it. This is a low zone here, and then this would be what they're calling the Whittier Fault there. More faults, San Pedro Basin faults. They're going wild naming faults. All right. Okay, let's talk a little bit more about the Newport Inglewood Fault Zone. We talked about this a little bit. One of the papers that we discussed suggested that the end of the Catalina schist occurred at the Newport Inglewood Fault Zone. So they were saying that all that uplift of Catalina schist that occurs in Palos Verdes and on Catalina stops at the Newport Inglewood Fault Zone. But our friends, Bob Bohannon and Eric Geis, said, well, this is where we think the Newport Inglewood Fault Zone is, and it doesn't seem to be that dramatic of a fault. So I'm telling you what I know about it, and it's odd that this doesn't seem to be much of a thing, so it's kind of puzzling. But that's the Newport Inglewood Fault on their seismic reflection profile. This is a study from 1987 by this guy, Egil Haxon from, of course, Caltech. And he's taking a look at the seismicity along the Newport Inglewood Fault. One of the things he did is he studied all those faults in that box here, all the black faults, and then he calculates in 3 dimensions. Instead of doing just where they occurred based on the overlapping circles, he did it in 3 dimensions and got their depth. And he's looking at the depth of those earthquakes in that box on the Newport Inglewood Fault, and he's saying they're mostly around 10 kilometers down. And here's a little histogram showing that they're from 8 to 9, so around 5 miles down, something like that. So he's studying the Newport Inglewood Fault Zone. What are the earthquakes like? Now, he did a whole bunch of, this was in 1987, so these are probably possibly all hand done. Here's the Newport Inglewood Fault Zone, and does everything look like a straight slip fault based on his focal mechanisms? No, it looks more complex. There are some things that look like a strike slip fault, but kind of a weird orientation. Which one of those? I mean, it's supposed to be in that orientation, right? And it's not really in that orientation. So that's puzzling. So the orientation of the fault planes is kind of weird. And also you're seeing reverse faults and so forth and stranger interpretations. So I looked at this plot and I said, well, doggone it, this one, if we go back, this one looks so beautiful. We looked at 4 beach balls here, and everything just made total wonderful sense. And then you go to that study from 1987, and it looks almost like chaos, this one here. And then I was thinking, well, the only thing I can think of is he may be including lots of smaller earthquakes now, and the little earthquakes may not be focusing the big tectonic motions that the larger earthquakes would. So the only reason I can figure that you get such chaos as he's showing here is that these are smaller earthquakes and they're kind of showing little cracks forming as opposed to the big ones. But I'm not really sure. Again, it would have been easier to jump to that slide. So the larger ones, the 3s, seem to have better behavior. Lisa Grant is a professor at UCI in seismology. Oddly enough, I was one of her professors when she was an undergraduate at Stanford. I just taught her a class. She doesn't owe me anything because she's done it all on her own. But it's kind of cool that I can say, oh yeah, she was my student. So she's a professor at UCI, and I was telling someone earlier, oddly enough, she's a seismologist, and she teaches in, I think, the public health department, because they don't have an earth science department at UCI. Anyway, she's done a whole bunch of studies on earthquakes in the area, including trying to trace the Newport Inglewood Fault south of Newport Beach. So you can very clearly trace the fault from Newport to Inglewood, but what happens to the Newport Inglewood Fault as you go south? And she did a study a number of years back where she argues it ties up with what's called the Rose Canyon Fault, and it extends down here like that. And they're saying that, anyway, it's part of the San Andreas system. We can skip that. Okay, let's talk about the Long Beach earthquake now. 1933, 123 killed by earthquake in Southern California cities. 4150 are reported injured. So here's Long Beach back in 1933. Now, oddly enough, so here's Long Beach here. This is thought to be the epicenter. It's 4 miles essentially south of the Huntington Beach Pier. Do you know anything about it, Gary? So the thing that I've been thinking about recently is I don't think it's even on the Newport Inglewood Fault. This is considered to be the big earthquake on the Newport Inglewood Fault, but I'm not even sure it's on the Newport Inglewood Fault, and I've never heard of surface deformation and so forth, like breakage or rupturing.
There's a little splay zone right there, I think, right about where that is. When the Rose Canyon comes into the Newport Inglewood,
I don't know.
close to that junction right there.
As far as I could tell, it's coming in, the fault's in about here, not way down there. But this was back in 1933, and this was one of the most, it was one of the most studied, but the fact is that they just discovered seismograms back then. So like the 1906, I think, was pre-seismogram, and this was post-seismogram. So they had their brand new seismogram, so I'm wondering if they just mislocated it. There were studies associated with the Long Beach earthquake where they were studying direction of tombstone tilting, trying to understand the earthquake, if they all the tombstone tilted in one direction, and so forth. So 1933 was a long time ago in seismology studies. And here's some of the damage in Long Beach. The reason they call it the Long Beach earthquake and not the Huntington Beach earthquake is Huntington Beach was just a bunch of oil, derricks back then. So lots of damage in Long Beach. All right, so that's an introduction to the Long Beach earthquake. All right, when is the next big earthquake? This is another relatively new science, is establishing earthquake recurrence intervals on and faults. It's called paleoseismicity. And I always attribute this to this guy from Caltech named Kerry C. And what he did was he would dig these trenches right across the fault zones, and then he'd try to find breaks in the earth, and then he'd date them with carbon-14, and he'd try to come up with a recurrence history of when there was earthquakes on a particular fault. So what they do is they dig these trenches, and then they'd look for evidence of offset of the layers in the trench, and they'd say, oh, an earthquake caused this in 1906, it says, based on their studies, and so forth. So they'd try to come up with a history based on the offsets that they observe, the dated offsets that they observe in these trenches. And so there's all sorts of complexities associated with it. We'll just skip. But here's an example, again, Caltech, Kerry C, of these earthquake recurrences. Let's see. So here's the date in AD. So you can see there may be 80 years between 1800 and 1860. Here's maybe 150 years here. So that's 100 years like that. So here's a span of 200 years where there's no earthquakes, maybe 200 years without an earthquake. But here you have 3 earthquakes in 100 years, according to these studies. So this is how they do paleoseismicity, and the results are almost always frustrating. Well, they'll say there's an earthquake every 80 years, and we haven't had an earthquake since 1933, so that's 90 years. So you're thinking, oh my gosh, and they say plus or minus 100 years. And then you go, okay. So what they're doing is important and valuable, but it doesn't narrow things down so you can, know when to buy your earthquake kit. Earthquake intervals for southern San Andreas Fault. This is from Lisa Grant again, 2010, showing this. She's got an 88-year recurrence interval, plus or minus, in this case, 41 years, based on her studies. All right, that was a little thing on paleoseismicity. Let's talk about tidal waves now. Now, there's this big thing where they talk about tsunamis versus tidal waves. Now, when we were growing up, we talked about tidal waves, right? And now they call them tsunamis. Tsunamis in Japanese means harbor wave, so it's a wave that occurs inside the harbor. But being a surfer, I just want to acknowledge the fact that tidal waves, true tidal waves, are pretty exciting. So what happens is when the tides rise from just normal lunar cycles, you have the water going up into these estuaries, and there's so much water that has to be displaced, you can get humongous waves associated with the tidal changes. Should I show you? Okay, I'll show you. So this is one of the largest tidal bores. I can't remember where it is, but it's just so cool. I'll show you anyway.
Sort of cut back right and,
so that's a
and
tidal,
pulled into the barrel on the right too and didn't make it.
So this is from the tides.
Just a weird experience.
These aren't
stood up
waves.
just enough to get inside the tube for a little bit.
Is it damn? Yeah, there we go.
Felt really good, like really like an ocean wave, but.
So those are waves going up. Is it? Did you say how did you know it was the Amazon? Did it say?
Because I saw a special on this and about the water reversing waves, and these guys watch for tsunamis.
No. These are not tsunamis. These are tidal waves. These are tidal bores. Tidal bore.
Go to them because the surfing is
excellent.
Phenomenal.
Yep.
They say.
But anyway, this is from actual tides, nothing to do with earthquakes, and I only show you because I love waves. These are also tidal waves in China. All right. So they get about a 10-foot tidal wave in China, and those people, I think, are getting unexpected drenching. Now, a tsunami is associated with an underwater earthquake where we have fault displacement, and what it does is it moves this block of earth upward, and that volume of water is moved upward, which causes the actual tidal wave, but it's called a tsunami. All right? And the most famous of those, we have to watch a little bit of this. I think this is the Japanese one. Maybe a commercial. Yep, commercial. But I've got it muted anyway. Ah, it's Katie again. Yay, Katie. All right.
In the Indian Ocean. On December 20th.
Okay, this is the Indian Ocean one.
The Indonesian earthquake had as much energy in it as the total energy consumption in the United States in 1 year.
This enormous burst of energy had been released in just seconds. Once again, the world had been reminded of the Earth's awesome power. In the last 50 years, scientists were finally able to confirm a solid link between earthquakes and tsunamis. Although the Earth may seem to be a solid sphere, beneath the oceans and continents it is divided into 8 major and many minor segments known as tectonic plates. Where they meet, they can grind and jostle against each other at fault lines, causing earthquakes. Geologists had long thought that the Cascadia fault line was incapable of generating a major quake. But Atwater's investigation has proved that it was highly active. The big worry for Atwater and the thousands of people who live in this region is that the Cascadia fault line bears an uncanny resemblance to another highly active fault line, the Sunda megathrust. It was an earthquake along this fault that was responsible for the Indian Ocean tsunami that killed nearly 250,000 people.
where we get two tectonic plates coming together, such as the case of the Indonesian tsunami in 2004, one plate pushes beneath the other plate and creates lots and lots of friction and tension and drags the upper plate down with it. And that process can take hundreds of years, even thousands of years. It's a very slow process. But eventually, the pressure of this one trying to push back up again wins, and it flips like that. And that creates a mega thrust, a sudden movement of the seabed. And that's what creates a phenomenal tsunami.
All right.
What does this strange look?
We'll skip that. Making earthquakes. We have 20 minutes left, so I think I'll get on with things. Here's a good one. Earthquake or nuclear bomb. Okay, both form body waves, and you can see an example here comparing an earthquake with P and S waves versus a nuclear bomb. North Korea detonated a nuclear device in 2006. A map of the region shows the location of the test, red star. Nearby earthquakes, blue dots, and seismic monitoring stations, white triangles. At the blah, 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 northeast China. Seismograms recorded during the explosion versus recent earthquakes. So we can tell nuclear bombs versus earthquakes, which is good. What's a little alarming in Korea is that with time, from 2006 to 2013, the size of their nuclear bombs has become larger and larger. And we can demonstrate that using seismographs. Another one is how to make an earthquake. There's a clear correlation between high fluid volume injection and recent earthquakes and recent increases in earthquake activity in Oklahoma and other states. The process of fluid injection activates old faults that already exist. The introduction of such high volumes of fluid increases pressures in the pores of the rocks deep underground, which in turn can weaken the faults and trigger earthquakes. There is a famous study done by the U.S. Geological Survey, or I think it was, well, they were part of it, in the 1960s. And here's where they injected wastewater into the ground, and here's the resulting earthquakes. So then they said, hey, let's stop injecting fluids. And you could see that the number of earthquakes diminished. And they said, let's inject like crazy. And you can see the number of earthquakes responded in accordance. So this was back in the 1960s. We know how to create earthquakes. So the idea is you inject water into the subsurface, that increases the pore pressure, and that allows the faults to slip more easily. By the injected water. Yes?
I think it was called Rangley Field.
Rangley Field, right.
But the thing is that they wanted to inject water to reduce the stress, strain on the fault, but then the problem is that if you have a big earthquake, you have an insurance problem.
So yeah, there's been talk of like, well, why don't we just inject water into the San Andreas Fault? I think there's a Wild West episode about this where they were going to inject water into the fault zone and cause the 10. Because we don't really know what sort of resulting earthquake you'd get if you just randomly injected water into a fault zone. But anyway, this was the classic study. And then since the fracking phenomena has happened, we've seen earthquakes in Oklahoma go from something like none. Here's where they started injecting wastewater into the subsurface. And here's the number of earthquakes that they're seeing now up to today. And here's the distribution of earthquakes that they're seeing. The red are the earthquakes, and the disposal wells are shown in black. So there's a spatial correlation between where the earthquakes are happening and the location of the disposal wells. Okay, so Oklahoma earthquakes after 2010, greater than 3.5 magnitude. So this is 15 years up to 2005. So almost none prior to the injecting of the wastewater, after the injecting of the wastewater. Okay, clear correlation. That's a great lead-in, thank you. Those are pretty small, but let's see how big they get. 5.8 in 2016. So here's an example of 4 earthquakes greater than 5. So 5, you're getting up into the damage zone. Okay, so they have had some very large ones associated with them. This is the same sort of map as this. By the way, these maps I created myself using that website that I was trying to show you how to use earlier. So it actually it can be done when you're not under stress. Goodness gracious, what is this? I think I just jumped. Where's the button? Yep. So that's the last. That's the last slide. Any questions? Yep.
When they measure the strength of the quake, what about the depth? You know, how do they measure the depth?
How do you calculate the depth of an earthquake?
Yes.
I showed you how to do the epicenter location. The depth calculation is more complex, so I avoided it. But there's a mathematical way of doing it as well. It's essentially what you're doing is you're doing that same calculation in 3 dimensions instead of just 2 dimensions.
Do we always have 2 waves? The primary wave and the secondary wave on the earthquakes?
Yes. Oh, and you also get the surface waves. You get the primary, the secondary, and then the surface waves.
So which ones are we normally feeling? The surface waves?
Yeah. The surface waves do all the damage.
Okay. And then the deeper the quake is, the fewer the surface waves?
No. No.
Not necessarily.
No. The other thing that we could talk about that I didn't was if your house is built on granite, you'll have a different shake characteristic than if you live in Huntington Beach, which is an old floodplain of a river. So if you're built on muds, your house is going to shake very differently than if you're built on very solid granites. So what type of rock that you're in is also of significance. Yep.
Has Oklahoma modified the way they're doing well now?
Good question. I suspect so, but I don't know. All I know is this data, and I didn't follow up. That's an excellent question, whether Oklahoma's changed their disposal well characteristics. Other questions? Yep.
So USGS has the... Wait. So that we can get it recorded. The Did You Feel It website.
Yep.
I don't know if everybody knows about that. But USGS wants us to tell them when we feel an earthquake. And so there, you Google, did you feel it? And you'll get there, and you can answer a few simple questions.
That's right. So if
citizen science.
So if you feel an earthquake, you can go onto the USGS website and say, I felt an earthquake at 2:22 p.m. on this date, and this is how much shaking I felt, and they will use it to construct the Did You Feel It maps. All right? Good point. Thank you. Yep.
Some years ago, there was a problem.
Microphone arriving.
Some years ago, there was a problem in Long Beach, and it was sinking, and they injected a lot of seawater. Did that cause any of this stuff to go on?
Excellent question. So as we all know, as you go into Sunset Beach, north of Huntington Beach, during the high tides, a lot of times the high tide will just flood the roads. And the reason for that is because they were sucking oil out of the Seal Beach oil field, and that caused the pore space to collapse, which means not only is sea level rising, but the land subsiding, so they had lots of incursion of the ocean. And so what they did to counter that is they drilled what are called injection wells, and they injected water to expand the pore space so it wouldn't be sinking so badly. What you're saying very intuitively is, does that increase the potential of earthquakes in Seal Beach? And I don't know the answer. We could test it by using this very technique where we'd go and look at Seal Beach, which is right down here, and then we could look at after they started injecting. We could actually do be a perfect term paper for a college student, right? Because you could go to this website, if you know when the injection happened, we could look at earthquakes before and after in that area. But excellent question. Yep.
Are there any incidences of liquefaction in Orange County and from earthquakes that you know of?
I don't.
I know there was a liquefaction incident from the Northridge quake in Redondo Beach. The harbor sections are kind of man-made. They're made out of sand with rock linings, and the buildings on those things all, collapse because of liquefaction.
Yeah, to be honest with you, I study sand mostly, and I study rocks. And I know a little bit about earthquakes because I study plate tectonic stuff, but it's not my specialty. So this is a part of a more detailed knowledge that I don't have. I apologize. Yeah, oh, yeah, in San Francisco.
But we have the soils that could have.
Yeah, definitely. Long Beach, you'd expected Long Beach, Redondo Beach, anywhere you have sloppy sediment. What liquefaction is when you shake something, the little grains of sand are kind of like happy together, but when you shake it, they collapse. What happens is they go to a tighter framework, and what it does is it frees up everything on top of it. So it's kind of what's called a compaction wave, where you have loosely consolidated sand, and during the shock of the earthquake wave, the sands collapse downward, which frees up the water in the pore spaces, and that's the liquefaction event. And that can cause huge damage during an earthquake. Like quicksand, yeah. Yeah. Any other questions?
Yes.
Yay, questions, love it.
Is there a direct correlation between the intensity of the quake and the expanded distance it's felt?
Yes. So the closer you are to the earthquake in general, the worse the shaking.
No, I meant how far out does it go? How far
Yes,
is it
you
being
can feel
felt?
larger earthquakes further away.
Way further.
But it's complex because they say, like, if there's an earthquake in New York can actually get earthquakes. They'll sometimes feel it in Iowa. So I think the crustal structure really allows. I think there's so many faults in California that the earthquake waves may not propagate as far, because I know that in the mid-continent they can go. A smaller earthquake can be felt hundreds and maybe even 1,000 miles away. But I'm winging it. Well, and the crust is very unfaulted and so forth. So there's definitely the distance at which you can feel an earthquake away is not like a constant. If it's an 8, you can only feel it at 100. It's very much variable, associated with I think it's on the complexity of the local geology.
Well,
Question?
thank you very much, and we look forward to another session. Or
one more section.
One
So
more.
the last one is what the ice ages were like in Orange County. And there was definitely, you're not going to believe how different it was. It was dramatically different, and I'll tell you all about it next time. Thank you.